But we're going to go a little different way. Let's start a little bit with what I'm going to call the nature of reality. You and I need to understand a little bit about hyperspaces. Hyperspace is a fancy word for spaces of more than 3 dimensions. You and I live in 3 dimensions. And we're not going to get into a lot of advanced math or anything, relax, but there are some insights you and I can glean from what is now understood about the reality we live in that will cut through most of the theological paradoxes you'll encounter. And so let's get into this. In school, either in plane geometry or trigonometry, you had triangles. And you had angles in a triangle. If you add up the angles in a triangle, what does it add up to? Anyone? 180 degrees. Good. No matter what kind of a triangle I have, 30, 60, 90, or 45, 45, 90, whatever, it always adds up to 180 degrees. Well, suppose that 2 of us go out to a very large field with a transit, and we lay out a very large triangle. We bring the angles back in, and they add up to more than 180 degrees. Well, that's what you expect from a bunch of dumb pastors or something. No. No, it turns out that we've encountered something. Did anyone here know what we've encountered? If we find a triangle with more than 180 degrees, what's happened? Yes? Curvature of the earth. Good for you. See, if you go into a navigation as a pilot or as a seaman or whatever, you'll take a course in spherical trigonometry in which you can have 90 degrees in each corner. And see, when you encounter something that seems to violate the rule, see, the rule we all learned in school, that the angles of a triangle add up to 100 degrees, is only true for a universe of 2 dimensions. That's why they call it plane geometry or plane trigonometry. It's only true for a flat plane, you see. If you have more than that, you're dealing with a convex surface. And if you have less than 180 degrees, you're dealing with a hyperbolic paraboloid. But I don't think that is something you're normally going to want to go into. But when you encounter something that violates a rule you've learned, one of the possibilities is that you've encountered a dimension that you didn't know existed. You see? And so it's that kind of insight that caused Dr. Albert Einstein, as he was grappling with the nature of space, to realize that space is not limited to 3 dimensions. And he developed his theory of relativity by recognizing that it really consists of 4, at least. The special relativity was 1905, which was length, mass, velocity, and time are relative to velocity observers. The general relativity in 1915 was that there was no distinction between time and space. We won't get into the math here, but the point is a physicist will speak of space-time. You can't speak of space and time separately. Time is a dimension of our space. You and I live not in 3 dimensions, in 4 dimensions, 3 spatial dimensions and time. And that's no longer just a conjecture. This 4-dimensional continuum that we now know we live in has been confirmed 14 different ways to over 19 decimals. And it happens to include an insight that gets around many of the problems we encounter. So we want to talk a little bit about this peculiar dimension that you and I are in called time, the nature of time. Time, it turns out, let's talk about this first of all. There are atomic clocks located at the National Institute of Science and Standards and Technology in Boulder, Colorado, and also an identical clock at the Royal Observatory in Greenwich, England. These are atomic clocks. They're accurate. Both of these are accurate to better than 1 second per million years. So they're as accurate as we know how to make clocks. They're based on the natural resonance of cesium. I won't get into all that. That's not important. They're just very, very accurate clocks. But here's the dilemma. The one at Boulder ticks 5 microseconds a year faster than the identical clock at Greenwich. Every year they have to make an adjustment. Why? Which one's correct? Greenwich or Boulder? The Brits or our federal government? I didn't mean anything by that. That's all right. Well, the answer is they both are correct. You see, both are. The Boulder, Colorado is at 5,400 feet altitude, and Greenwich, England is at 80 feet of altitude. And the gravity is different at both places, which means the time, it's not the clock problem, the time itself is different at each place. The atomic clocks, if I had an atomic clock here on the platform, and I raised it 1 meter, it would speed up by 1 part in 10 to the 16th. Not a big deal, but it's measurable, predictable, and confirmable. In fact, they actually did this with an aircraft experiment back in 1971. They put an atomic clock on a plane going around the world eastward, and compared to one at the observatory, it lost 0.059 microseconds, or 59 nanoseconds. They did the same thing with one going westward around the world, and it gained 273 nanoseconds. Not a big deal, but it was exactly what the mathematicians had predicted because of all the factors involved, the motions and the gravity and so forth. I'll give you another example. This one's, I think, kind of fun. If you read a textbook in physics on this subject, you'll discover that they'll usually talk about these two imaginary, hypothetical astronauts. They're both born at the same instant. And we're going to send one of them to the nearest star. The nearest star to us happens to be Alpha Centauri. It's about roughly 4.5 light years away. If you look at the night sky, there actually is a star called Alpha Centauri, and that's the nearest one to us. And it is about 4.5 light years away. We're going to send one of these guys, leave one here with us. We're going to send one of them to that star and back. Now, we're going to send them there at half the speed of light. This is obviously theoretical. And so that means that here on the Earth, it's going to take him, since 4.5 light years, going half the speed of light, it'll take him 9 years to get there, 9 years to come back. So he'll return in 18 years. Are we together so far? Okay. But what time is it on his clock? He's got a wristwatch around his wrist. What is it? Tally. And you can tell this by the Lorentz transformations, which I won't bore you through, but there is a correction factor. It turns out when he gets back, it'll only be 15 years and 7 months. In other words, he'll return 2 years and 5 months younger than his twin brother. And if that doesn't bother you, you weren't listening carefully. Two identical astronauts. One goes on the trip, one doesn't. The guy that gets back is younger than his twin? Man, that's interesting. Okay. To dramatize this further, let me go a step further. Let's assume we had sent him at 99.99% of the speed of light. Let's assume for the moment that'd be possible somehow. That would make the round trip 9 years on our calendar, but it would only take 33 days on his calendar. And so let's hope he bought some Microsoft stock on the way or something. But anyway, okay. See, time itself is a physical property. That's the point. We don't think of it that way, but time is a physical property and it's not uniform. It varies with mass, acceleration, gravity, among other things. Well, here's the question then. Is God subject to mass or gravity? By the way, you and I live in more than 3 dimensions. There's apparently 10 of them. We're going to talk about that in one of the subsequent days on the creation when we get there. See, you and I think of time as linear. When we were in school, the teacher put a line on the blackboard from left to right. The left end was the beginning of something, the birth of a famous person, the founding of an empire. The end of that line was the collapse or end of that empire or the death of that person or what have you. It's a timeline. How many of you made timelines in school? Sure, we all have, sure. Incidentally, this time has an arrow, by the way. Time is a very peculiar dimension because it's not two ways. We can move forward and look back. We do that all the time. We move forward and look back. We can't move back, nor can we look forward, can we? Well, God can, but we can't, okay? When I'm in California, I usually ask, how many of you remember tomorrow? When I make this talk in California, I was guarded when I asked that question. There is another property of our existence that we're going to get into in subsequent days called entropy, which is a fancy or mathematician's word for randomness in a sense. Maximum entropy is maximum disorder, maximum randomness. When you organize something, you are decreasing its entropy, if you will. It's interesting that the universe is going from order to disorder. That's what we mean by the second law of thermodynamics. The universe is winding down. Thermodynamically, it's winding down every other way. Every field of science recognizes what they call the law of entropy in their observations, except only one field of science chooses to ignore it. If you're in physics or any field of science, especially information sciences. The only field of science that chooses to ignore entropy, the entropy laws, is biology, because they have a problem, because they want to create order out of disorder by itself. And you can't do that. And we'll talk a lot about that as we get to the discussion of life going on. But we'll talk about, we're going to map, ultimately, the 6 days of creation in an entropy map when we get to day 7.